Good afternoon, everyone. I'm Alan Guwy, and I'm from the University of South Wales, and I head up the Sustainable Environment Research Centre there. And I'm going to tell you a little bit about where we are. Okay, so the Sustainable Environment Research Centre is a multidiscipline one, and it sits in the Rhondda Valley, which actually is the heart of a big coal mining community in the last industrial revolution. So it's a very relevant place for us today to talk about a new paradigm in low carbon energy. And we carry out research in many different areas around the energy and environment R&D challenges, but focusing on waste, energy and water, and quite a lot of that is at the interfaces. We carry out mainly applied research, but we also have a lot of work in the hydrogen area, which I'm going to concentrate on today. And you'll see there we've been very lucky over the years to be funded through the framework programs. So from 1991, and most recently we've just been funded on a program with SNAM, which is entitled H2 Shift, which I will talk about later in my presentation. Okay, so this is the Hydrogen Research Centre. It's situated, I haven't got the pointers, at Port Talbot. And this was a fairly unique building. Back in 2008, we built this, and it generated hydrogen from PVs, and we've been refueling vehicles since then. It's rather difficult to. Oops. So today I'm going to talk about the role of hydrogen in low carbon future, and I'm going to talk about that in the perspective of the region that we're situated, and then in the UK, and some funding opportunities that I think are relevant for our collaboration going forward. So hydrogen, we know, is the most abundant element in the universe. It's all tied up in molecules, water, hydrocarbon, biomass, so we're going to have to extract this hydrogen from these molecules if we're going to use it. Although recently there's been developments, which I'll talk about right at the end, which may mean that we can actually mine hydrogen in the future. And what makes hydrogen a good energy vector? Well, it's got the highest energy content per unit mass of any chemical fuel. It burns and produces no pollution, just water. It's got a heating value that is 3 times greater than any hydrocarbon fuel, and it can be produced from a variety of sources. We've heard already about nuclear power and how we use those electrons to produce hydrogen, but also natural gas, which is where hydrogen is mainly produced these days. Over 98% of the hydrogen produced is through natural gas, steam, methane reforming. Biomass, and of course through renewable power such as solar, wind, and hydrocarbon geothermal power. They can all be used to produce hydrogen. And some years ago, as part of the team that generated this document for the Royal Society, looking at the various low-carbon routes to hydrogen at scale, and it's still relevant today. The insights is worth a look. And the schematic there on the right shows the various sources of energy that can be used and the end-use technologies, including heavy industry, heating, transport, agriculture, and ammonia will play a very important part in hydrogen use in the future as well. So there are there are a number of ways in which hydrogen can be made, and they've been given various colours. I'm not particularly in favour of that colour coding, but if we quickly go through them. So brown hydrogen is through the production of coal. It can be used, it can be called black hydrogen as well. Grey is through steam methane reforming. As I said, this is the majority of the hydrogen today is produced this route. Blue hydrogen through steam methane reforming, but the capture of that CO2, so either capturing it and storing it in geological structures, or you can use it, as we've seen just in the previous talks, in chemicals. And turquoise hydrogen is a similar way in which methane is pyrolyzed, but instead of needing to capture the CO2, we have carbon as a solid. And we mentioned already pink hydrogen from nuclear power, and obviously the green hydrogen, which is the main focus of attention these days, is to green our hydrogen production from renewable energies. And yellow hydrogen is emerging forms of hydrogen such as direct solar power electrolysis. And as I mentioned, there is an opportunity to mine hydrogen in the future, possibly, and this has been labeled as white or gold hydrogen. But we can see here that the renewable electricity forms, including nuclear power, I would class in that, has a massive advantage when we are decarbonising the hydrogen futures. So I'm going to concentrate on three main forms of hydrogen production. As I said, the grey form of hydrogen, which is through steam methane reforming. It's well-versed technology. It's all over the world. It takes place at 700 to 850 degrees C. Current efficiency is around about 70%, and future situations and research predict that this will increase to over 80%. And of course, this produces a lot of CO2, and this can then be captured, as we said, captured and stored geologically, and then become this blue hydrogen, which is up big debate at the moment in the UK and in Europe. Oops. So through electrolysis, with splitting of water, it's again a very tried and tested system. Technologies include alkaline, proton exchange membranes, anion exchange membranes, and solid oxide electrolysis cells. Their potential efficiencies range between 70 and 80%. The big advantage of these systems is that they're modular, so they can go from small buildings to large installations at megawatt scale. And the greenness of this hydrogen really depends on the amount of where these electrons come from, and that is the key. I'll talk to you also about biological hydrogen production. This is potentially a negative route for production, negative carbon. And the one I'm focusing on here is anaerobic digestion. This is a technology that's been established worldwide. It actually accounts for 5% of the natural gas consumption in Europe, so a considerable amount. And the conversion technology here uses technology that's already in existence. So where we would normally use natural gas through steam methane reforming and then capture that CO2 to make the hydrogen, we do exactly the same but use biomethane. And in that sense, once the when the CO2 is captured, because that CO2 has been biogenically formed in the first place through biomasses such as sewage sludge, municipal food waste, it effectively becomes then a negative route to hydrogen production. And this, and taking example of sewage sludge, there is currently 45 million dry tons of sewage sludge produced annually, and there's 10 megatons of that is in Europe alone. And globally, this is going to increase with population, and as the population demands more or better sewage treatment, the forecast is that these materials will increase by up to 50% by 2050. And we've been working on these technologies for best part of 2 decades, and at our group, and we've looked at splitting the technology into 2-stage AD systems, where we make biohydrogen in the first stage through Clostridia. That bacteria breaks down these biomasses into CO2 and hydrogen, making carboxylic acids or volatile fatty acids as an intermediate. These are then fed to an anaerobic stage methogenic reactor, which is fine-tuned just to make methane. That methane and CO2 is then taken to steam methane reforming, and hydrogen is then produced. And you can see from the diagram underneath that in fact we can increase the methane production by almost 40% in the case of municipal food wastes, and we can do, if we want to reduce the footprint, we can still increase the methane potential by as much as 17%. So rather than concentrate on efficiencies around steam methane reforming, we've looked at the biological production. We've had a number of pilot plants funded through the last 14 years or so, and in most recent times we've been funded through BEIS to look at how we would scale that up at a full scale. So how can hydrogen help build a climate resilient society? Well, it's a really complex question to ask. It's a interconnected option answer. Undoubtedly, hydrogen will play a massive role in decarbonizing power systems, because when the sun isn't shining, you need to capture that energy. When the wind isn't blowing, you need to store that energy somehow. And hydrogen is certainly going to play a role in that. Obviously, with transportation, in recent times, battery electric vehicles are really stolen the march over any hydrogen vehicles. We have been a few in Wales and across the UK, but I think their transport will, or hydrogen will figure in transport at HGV levels and larger vehicles that need to go further distances, and also in the heat, in the production of heat. And this is something that is a really hot topic in the UK at the moment. Most boilers are configured to be able to utilize up to 20% hydrogen, so even a small amount of hydrogen into the existing grid can be used at the moment, but that would, at 20%, that would be a huge production of hydrogen. And then, of course, hydrogen would be used significantly in the difficult industries to decarbonize, such as cement and steel. And in Wales, we've been lucky enough to be part of the City Deal. It's a nearly £60 million programme run by the local council, Newport Talbot Council, along with our colleagues in Swansea University. And this is, of that, there's about £2 million capital fund. There's a hydrogen stimulus project, and this utilises photovoltaics on this building. To your right there, there's a new council building, And when the building's not using the electrons from the photovoltaics, they will be transferred to the hydrogen centre where we will refuel vehicles. And we're working closely with the South Wales Industrial Cluster, which we're the academic leads for, and a newly funded project called Switch, which is about buildings as power stations. And the South Wales Industrial Cluster is a good example of how the role of hydrogen, how hydrogen can play a significant part in a region. Along the South Wales coast, we have a lot of companies that are emitting huge amounts of CO2. In total, about 16 million tons of CO2 per year is emitted. And we have all these companies now as part of a consortium where we're working with them to look at all the different ways in which we can decarbonize their industries. And hydrogen plays a significant role in that. And a good example of one of those projects is a project that RWE are building, looking at offshore floating wind to produce renewable hydrogen, green hydrogen, incorporated into the gas grid system through steam methane reforming and capturing of the CO2 compressed into shipping, and then those ships are then taken up to regions where there is then carbon capture storage, because in and around the South Wales coast there is no such geological structures to be able to store that hydrogen. And this is part of the South Wales Industrial Cluster is just one of these industrial clusters in the UK. There are 5 others, there's 6 in total. And the funding for the IDC programme is nearly £500 million, so it's not short of money. And the industries have bought into this in quite a big way and matching that funding. And you'll see that the South Wales cluster is about the second largest. The size of the circles denotes the amount of CO2 emitted in these regions. And unfortunately for South Wales, this circle is going to reduce in size because Tata Steel have just announced that they're shutting 2 of the blast furnaces, which constitute 15% of the CO2 from the region and 2% for the whole of the UK. So it's a real significant blow for that region. But one might argue that it saves a lot of CO2, not so good for job prospects and the economy, however. And if we look at the Hydrogen Council is predicting by 2050 that hydrogen could actually, low carbon hydrogen could actually be a potential level comparable to electric generation currently. There's a big sort of margin of error there, but you can see that that prediction, and it is only a prediction, does show that there's going to be a rapid need for hydrogen production to decarbonize industry, power, heating in our homes, and of course transport, not least aviation. And in the UK, the research councils have been very proactive in setting up new hubs, good for collaboration in the context of our collaboration with European partners and France. So there's 2 main centres that have been funded last year, HIACT and UK HiRes. And HIACT is looking at the integration aspects of the energy transition, whereas a UK HiRes is looking at production, storage, end use, safety, environment issues as well. Both those projects are £10 million or so over 5 years, and they have been 50% matched with industry funding. So again, a very strong commitment from industry in these research projects. Another program that has been launched recently is the Place-Based Impact Accelerator Accounts, and we are at the University of South Wales are involved in 2 of these. I think there's 6 in total. One that I mentioned already, Switch, which is looking at buildings as power stations, and hydrogen will figure significantly in that program. It's a 4-year program with £4 million worth of funding, and again, a 50% match from industry. And GW Switch is led by Bath, is the Great Western Supercluster of Hydrogen Impact for Future, rather grand name. But again, that's looking at production, hydrogen storage, conversion and transport. I did mention that we were asked to sort of highlight any European funding from the framework program. We are involved in H2 Switch. The lead company is SNAM. There's 13 partners across 6 European countries looking at advanced electrolysis, biohydrogen and direct solar hydrogen production. We're hosting Protium's electrolyzer development as an open test bed. Just 2 more slides. A big sort of discovery, I guess, is the hydrogen deposits in the Lorraine Basin, 3 kilometers down. Whether it can be successfully mined, who knows? But the estimates are really significant, and this is backed up by US Geological Survey, who estimate that there could be even billions of megatons of hydrogen in geological structures. So this could be a real game changer. I'll just flick through. The Commission is really backing hydrogen with significant investment in 2 programs, High to Tech and High to Use. And in summary, hydrogen will be critical, I think, in the transition to net zero. Hydrogen and hydrogen-based fuels will help decarbonize the hard-to-abate industries, mobility, and power generation. The demand for clean hydrogen is growing, but it will need to grow much faster if it's going to meet the 2050 zero emission targets. More research, innovation, and larger scale deployments, not demonstrations, will help speed this up, and we've seen some of those in the region that we're working in. And luckily, this all needs collaboration between countries, industry, and academia.
Okay, thank you very much, Alan. Thank you. Okay, we'll take the questions obviously at the end, so please come.